So during the earlier class, yesterday's class, we have learned the general structure of message authentication code MAC. We also compared with encryption decryption. We also compared with hash algorithms. We found MAC differs from hash through one um, component, that is usage of the keys. All right, that's the only place you could see the difference. Otherwise the objective was almost same, that given a bit of input, given a size of big size of input or m number of blocks, original message can be of any size. You will be able to create a fixed size hash or digest. All right, that is what our MAC, MAC. All right, so these are the things which you have learned today. Now let's just progress a little more on that, to see what are the requirements, specific requirements of message authentication code, and also if time permits, we'll learn about hash-based message authentication code creation. Right, we call it as HMAC. Yeah, let's proceed. As we know, a MAC is known as a cryptographic checksum, right? So we know about checksum. This is a cryptographic checksum, which takes two things. One is the key, other one is the message. Okay, and you create something called MAC. This key we are using today, nothing new. It's a tag. Okay, the message authentication code in short, or in other word, it is given a new name called tag. Okay, so we know what is M. M is a variable length message, and K is the secret key exchanged between the sender and receiver. All right, and then you got your MAC, which is also called as tag. This is known to us, nothing new. What is to be learned from this? What are the requirements for message authentication code? Okay, but before getting into the requirements, let's have a small discussion on attack on the confidentiality. Because we use the secret key, we need to talk about the attack on the confidentiality. So what is the attacker is going to do in order to find the key? Because key plays a major role in the case of message authentication code or tag creation. So any attacker will always attempt to find and to deduce this key. Okay, so that's called attack on the confidentiality. In that case, if we use a k bit key, okay, if the k may be 10 or 20 or 128, whatever it is. So if the regular system, the MAC system uses k bit key, and attacker requests approximately 2 power k. Okay, approximately he requests 2 power k possible keys to be used to find out. Okay, you can exactly, if you want to say, it's going to be 2 power k minus 1. Okay, so a brute force attack requires this many attempts for a k bit key on the worst case performance. If it is a best case, that's a different story. Okay, but for a brute force attack, he has to find the key, and if the key length is k, he needs this many rounds of iteration to find the key out of it. All right, but this is what we have learned so far for our cryptographic concepts. Is it same for MAC? Because apparently, when you look at your message authentication code and the encryption, we learned one statement yesterday. The only difference between the encryption, decryption, and your message authentication code is on the reversibility. Whether the ciphertext can be reversed, then it is encryption, decryption. If the message authentication code cannot be reversed, right, then we call it as a MAC. That's the fundamental difference which we saw yesterday. All right. Having said that, we are not going to reverse it. Having said that, can we have the same logic, or is it the strength of MAC also is very similar to how we are doing the cryptanalysis? Probably we'll ask our friend. He says no. Okay, so that is not going to be same. The cryptanalysis or the strength of MAC and the encryption decryption algorithms are not going to be same. There are certain discussions on that. So I have deliberately made this slide blank because I wanted to write some points here and explain to you. When you look at the MAC, we have one point which is another difference between MAC and your encryption decryption. Suppose your original message is of size M. In the case of ciphertext, you will get the same size of message as the ciphertext. Suppose it has got n bits. Original message has got n bits. Your ciphertext also will have got will get n bits. You remember that? All right. Now, what is the case with Mac? That is not the case. In Mac, whether your size is n bit or no l bit or whatever it is, if it produces a fixed size, let me say m, if m is the size of your Mac, in other words tag, whatever may be your input size, it is going to give a fixed size. For example, SHA-12 in the case of hash. Okay, SHA-512 will land whatever may be your input size. Only thing is it should be in the multiples of 1400 1024. All right, that's what we remember. And it is always going to produce 512 bits as the hash. Whatever may be your size, the size of the input message, it's going to produce the same one. Now, when you talk about the Mac, the other difference between hash and Mac is the usage of key, as we know. Now, let's see that the key is n bits, maybe small k. Okay, the key contains k bits, and n is the size of your tag. In case if the size of the key is greater than n, okay, if the size of the key is greater than n, what is the number of possible keys which are available? You have got 2 power k is the number of possible keys. How many possible digests are possible or tags are possible? 2 power n. All right. Obviously, this size is bigger than this size. In other words, more than one key. All right. More than one key has to produce, will produce the same message digest. Isn't it interesting for the same message? Yes, that's true. Let's take the case of k as probably 5 and n as 2, just for instance. Okay, so 2 power k is 32. You are getting 32 possible keys. So here n is 2, so you will have only 4 different message digests, which means 32 keys at different first key, second key, third key, fourth key, and so on, up to 32 keys will produce probably 1, 2, 3, 4, maximum 4 number of digests or 4 different tags. In other words, first key, fourth key, 25th key, and 31st key, they all may produce the same tag, because this many number of keys can be used, but they all can be mapped with only 4 different tags. Do you understand that? Yes. Here, when I was thinking initially when I was exploring about Mac, I felt this is going to be the downside. This is going to be the bigger. No, this is going to be vulnerable to attack. Okay, but when I was doing the analysis, when I looked at the textbook, then I know it was clear that this is not going to be a weaker one. Probably this is going to be the strength of your Mac. So let me tell you how this can be the strength of the Mac. All right. So let's go for the brute force attack. Okay. On this Mac, I just want to go for the brute force attack. This is the number of possible keys. This is the number of possible digest or the tags which can be created. So initially you will go for 2 power k possible number of attempts if you want to go for a brute force attack. Okay. So you will have 2 power n different tags. Now you will be able to find some number of keys, some number of keys which will create the same digest. That's what I have told. Okay, key 1, 4, probably 25 and 30, they all are going to give the same tag. In that case, when you are using 2 power k number of keys, there is a possibility that 2 power maybe some good number of keys are going to produce the same tag. All right. Now we are other keys, for example, let me say L number of keys. Okay, 2 power L number of keys, which is less than 2 power k, obviously. 2 power L number of keys are producing the tags which are not your intended tag, because as the attacker, as the brute force attack, you got your message authentication code and the message which is unencrypted. Remember, because we in the basic model of your Mac, this message is not encrypted. We don't go for the encryption and the key. All we have is the message and its corresponding digest are appended and sent. So the attacker has access to this as well as the digest. So he has got access to M as well as the corresponding tag. So for the specific message M, we go for 2 power k possible attempts and we get 2 power n number of digest. Out of them, few will be matching with T. So that is going to be roughly, this is going to be 2 power k minus n, because the remaining are not going to produce the same tag. You can remove that because they are not going to help you. All right. So how did I arrive at 2 power k minus n? You got 2 power k possible keys, but you are getting only 2 power n digests. Obviously, you will get this is equal to 2 power k minus n, as you know. Only this many keys are going to help you to find out the key. Is it all over? No. Still, you have got 2 power k minus n keys to deduce. All right. But if you use the normal cryptanalysis, if you are not going for mac, if you are no, suppose we are going for encryption decryption, our brute force analysis is done, because every individual key is going to produce unique ciphertext. So at a particular point you will stop your iteration and your problem is solved, the attacker's problem is solved. But here, because 2 power k minus n um, keys are producing the same digest, you still haven't come to a conclusion. You will go to the next iteration, where you will use 2 power k minus n possible keys to produce the digest. Now what will happen? Another n keys will be deduced, because they are also going to produce the same digest. So you will have again landing k minus 2 times n keys to be subtracted, and eventually you will end up in having one key. Right, that one key will produce, will have, that one key has been used by the actual sender to calculate the mac. All right, one thing you should remember, for the second iteration same message will not help, because the same message, if you are using the same digest, is going to have going to be the output. So you will go for another message, another combination like this message and the digest combination, and you will do the iteration. Then you will go for the third message m3 and the corresponding tag, and then you go for the calculation. All right, eventually, not in the third round or fourth round, but at some point of time you will end up in getting one message, one key, which produce the corresponding digest, which you can check with the earlier messages. Yes, you will get it, because this key has already produced the digest, the tag already. Okay, this is how this is uh, the advantage of having the mac. Okay, not advantage, I would say the difference between your crypt analysis on mac and the crypt analysis on your ciphertext. Right, it is not easy, it is rather difficult or tougher than doing the crypto analysis on the crypto system. So doing the crypto analysis on mac is going to give you a nightmare, as compared to your normal crypto analysis. Hope you have understood what I'm trying to tell you. So having said this, what are the requirements of message authentication code? There are three things. They are not very difficult to understand. I'll help you to understand that. Yep. So the MAC function should satisfy the following requirement. There are three things, as I said. First one is generic, which is mandatory. If an opponent observes, okay, yeah, if an opponent observes M and MAC of K and M, that's what I have said, the message and its tag, because it is not encrypted. It should be computationally infeasible for him to construct M dash such that which produces the same MAC. This is what we have learned for hash LS. That's applicable to MAC as well. Okay, first point is done. A MAC of KM, so okay, your tag creation or the digest creation should be uniformly distributed. All right, in the sense, for randomly chosen messages. Okay, two messages are randomly chosen. Maybe the neighboring message, or they are some different message. M could be welcome, M dash could be Karunya, and so on. Some random texts which are chosen, the messages taken. The probability that the tag which is created for this and the next message is 2 power minus n, which means it should have a lower collision rate. It cannot be zero, because as I said, a MAC is going to be many to one mapping. Many messages will produce the same digest. So but on the other hand, the requirement is the probability should be very, very less, where n is the number of bits in the tag. Okay, if the message digest size is n, the probability should be 2 power minus n. Okay, that is 1 by 2 power n. Okay, the third one, let m dash be equal to some transformation. Suppose your m is 1 0 1 0 1 1 1 0. Okay, and you create, this is m, and you create m dash which is not M, but there is a small change. What could be the transformation? Okay, flipping the last two bit. It's a simple function. Okay, the simple function flips the last two digits. So what will be the M dash 10101101? Okay, this is M, this is M dash we have created. In that case, the probability of these two to be equal is again going to be 2 raised to minus n, very similar to the second one. Okay, because the first one is randomly chosen, second one is you make minor change or probably you make a small transformation in the message, but still the collision should have the probability of maximum of 2 raised to minus n. All right, that is the requirement of message authentication code. I hope you could understand. Now we have come across three major things. One is the cryptography, the other one is SHA, and SHA, not SHA, hash, and the third one is message authentication code. For cryptography, we have learned AES, DES, RSA algorithm, and connected to that we have got Diffie-Hellman key exchange and elliptical cryptography. For for hash algorithm, we have learned SHA, but I'm yet to teach SHA-3, which I'll be teaching you shortly. Now we have learned about message authentication code as well. It's better if we learn some message authentication code algorithm also. For that, we go for MAC based on a hash function. We call it as HMAC. We also have got cryptographic based MAC calculation, that is called CMAC, but fortunately or unfortunately that is not in our syllabus. So we'll concentrate on HMAC, where MAC is based on MAC is based on hash. Very simple, sir. Take the hash algorithm, hash method, take the MAC, or in the MAC, use the hash algorithm as a mixture. Okay, put them together, you get something in your bowl. That is what happening in the case of HMAC. So we are going to create MAC based on the hash. Okay, by looking at the diagram, you can easily understand that. But what's the design objective for that? I'll read one by one. To use without modification available hash function. That's the great expectation, right? When you go for the MAC, what is the difference between MAC and hash? We have learned MAC uses the key. Okay, otherwise logic is same. The same digest size is also produced. Okay, so the first design objective says, sir, you go for MAC, whatever you want you do, but use the hash function without making any change. What are the advantages? All right, the first advantage here is given as the second step here, second objective here, to allow easy replaceability of the embedded hash function. Okay, suppose you are using SHA-512 and for some reason you see SHA-512 is slow or it is compromised. Okay, we wanted to go for a better one or easier one. Our objective is really smaller. We should go for complex SHA-512. I can go for even a SHA-128 if it is available, or MD5 algorithm, something else we want to use. In that case, it is easy for you to change your MAC. Okay, that's the second objective. That is actually the first sub objective of the first one. Okay, there is another point which also supports to preserve the original performance. Okay, instead of going for a new hash algorithm or new method, hash is already available, which has proven its security, its strength against the attack. Why can't you use it, sir? Instead of making something else and still there is a problem with, and you have to do the performance analysis or attack analysis. All these kacharas are not required, right? So you use the existing one. That's the second sub objective of the first one. Okay, and also you should have some ways to use the handle to use and handle the secret key, because MAC is based on the key in a simpler way. It should not be it's not too much. Okay, and the fifth one is a little crucial to have a well understood cryptographic analysis of the strength of the authentication mechanism based on reasonable assumptions about the embedded hash function. Okay, now this I'll tell you in a small statement what this statement is trying to tell you. It says the strength of your MAC is based on the hash. Okay, so a simple mechanism is as that of. So if MAC is broken, you should always blame the hash, the underlying hash. That's the meaning of that. Okay, now this is what all about your HMAC. What is that HMAC? MAC based on hash. I'll tell you what is happening here. It is very simple. Look at this. Is it right in here? You look at this. What's happening here? You got the message. Okay, the message is denoted by y0 y1 up to yl minus 1. B is the block size. Please write it correctly. Where? Yeah, yeah. B is the block size which you have got. All your Y is all the original message. Okay. Y0 is the first block in the message. Y1 is the second block. This is the YL minus 1. This is the last block in this message. Okay. And this goes to the hash. Recall our SHA-512. Okay. It takes the initial value or initial vector I used to say, which is of n bits, because what is that n bit? N bit is available in the buffer in the case of SHA-512. There are 8 registers. You remember? Yes. N bit is the size of your digest. So your output also will be n bits. All right. So what happens? Your hash is taking the original message and the SI. I'll tell you what this SI is, and it creates the hash. So in fact, it is creating the hash of message, but SI is included just to create some confusion, and that's the only difference. So if we don't have this portion, if you probably hide it, okay, hide this portion, the rest is going to be simple hash. Your message is going to the hash algorithm. You have got round function. In the case of SHA-512, there were 80 rounds, as you remember. Then the output is coming and so on, right? So from that you got the hash. So this is going to be your digest, intermediate hash value. Okay. And again, another steps, another setup, same setup, ditto same. You got the hash running, having the initial value of n bit. You produce the n bit, which is the tag. In this case, this is HMAC of m. Why have I used the k? Because that is the difference. Okay, we are using the k also into the hash. All right. Now all we need to find out is what is happening here, what is happening here. If you could understand these two, HMAC, that is MAC based on hash, is done. Okay. So for that, what is H? H is the embedded hash function. Could be SHA-512, MD5, any hash algorithm. We know that. IV is the initial value. We know that. This all belongs to hash. Okay. And M is the message input to HMAC. Okay. That is the message, original message for which we need to find the tag. I'll just check the time. I got a few more minutes. Okay. And you got all these messages are divided in different blocks of yi. Y0, Y1, Y2 up to Y is some n number of. Okay. L is the number of blocks in M. Okay. This is 0th block, first block, and Lth block. Okay. All right. Then N is the length of the hash code produced by embedded hash function. Yeah. That is what your output. So size of your tag is n bit. Okay. Then K is the secret key, because MAC uses the key. So K is the secret key, and it also says that the size should be greater than n and so on. Okay, but you should know K is the secret key. Is that all about? No, we have got something called the K plus, which is key plus something. What is that key plus something? K is padded with 0 on the left, so that the result is B bits in length. Okay, what is the B bits? Where is B? Number of bits in the block. So K size is changed, is increased, so that its size is equal to the size of the block. Very simple, sir. If the block size is 24 bits, your key is 18 bits, you will add 6 zeros. Simple. To create K plus. Otherwise, it is simple as a K. What is that iPad? So the size of K and the size of iPad should be same. Okay, input padding should be same, which goes to the XR. What is that iPad? It is 36 in hexadecimal repeated B by 8 times. Okay, so if you have got the size of the B is the size of the block size, that is divided by 8 to get your iPad size. That is 36 in hexadecimal. How many times you want will be just copied next to next. Okay. Similarly, OPAD, that is 5C in hexadecimal. This is all the design criteria which were designed. All right. So you have got iPad, you have got OPAD. These are the two values. And this K plus, that is where input key padded with 0, and the iPad, which is the hexadecimal, which is the binary value of 36 in 36, which is in hexadecimal, repeated this many times, is given as the input. So you got the XR to produce SI. This is the new point component which we are introducing. This and the next one are introduced into your hash, otherwise it's hash. So that becomes your zeroth block just before your input. That is why in the hash you say si appended with m, and then you calculate the hash. That is why it is denoted like this, otherwise it's going to be same. Okay, another statement in another step, you got your k plus, same thing. I have just said what is this opad XOR to create the b bits, that is given as s0. Okay, so what is happening here? Here it finds out the hash of si appended with m padded to b, because if the number of bits in the n is lesser than b, then it's padded with b, padded to b bits, again zeros. Then you have got your s naught. These two combination, these two appended to each other, is going through the same hash algorithm once again to create the output. Okay, and you got your tag created here. So what is the tag here? The hash of k plus xr opad, yeah, okay, and then which is embedded, which is appended to hash of k plus or opad appended with message, original message. Okay, now this should reveal that something can be pre-computed, something has to be completed during its execution. Okay, so this is the overall structure, very simple one. Hash appended or something is prefixed with your mac, which is supplied with key. Okay, this is very simple. Now how are we going to efficiently implement it, that matters, but I should remember k is a fixed value, ipad is also the fixed value here, because k is the key. So this xr value, this si can be pre-computed if you understand it correctly. Similarly, this also can be pre-computed. This is going to reduce the time which takes to compute the tag value. That is what given in the further slide. Okay, how are they implemented? This component is pre-computed, and this component is also pre-computed. This, the second half, is actually computed during the execution per message. Okay, this is computed per message, so that this increases the speed of your tag computation. That is what happening in the case of HMAC. All right, have I got anything more? Yeah, final slide probably today. uh, um, a little bit discussion of the security of the HMAC, MAC based on H. Again, very simple point, only one point. The depends on the strength of the hash function. Okay, if you look at the whole of this hash implementation, there is nothing critical, sir. Probably this will reveal you. This is this is pre-computed. Sorry, this is not makes some. Okay. Yeah, it's working. Yeah, so this is pre-computed. These things are pre-computed, but these are the only things which are going to be computed. So hash is the main work which is happening even in the case of Mac. Okay. Hence, the security of HMAC is depending on the strength of the hash function. Um, so what is this successful attack on HMAC? Simple, sir. You are able to compromise hash. That's what written here. So it is equivalent to successful attack on HMAC is very well equal to either the attacker is able to compute the output of the compression function even with the initial value that is random, secret, and unknown, which means IV has nothing to do with that because you are able to compromise hash. The attacker finds a collision in the hash function even when IV is random and secret. So that is again is depending on the hash function, because hash says that there will not be any collision. Okay, even if there is a collision, then again we say HMAC is compromised. Okay, yeah, that's all I have got for you today on the HMAC. Probably we may have to learn about digital signature standard and digital signature algorithm in the next class.